Say for instance, I do anything for love. Me, I don't shoot bang, but I don't know, no. So no time. And if you say you know, do I go and die? Me, I don't belong, but I don't know, no. I'm on a radar. I go take flight, and I go fly to you. As you day waste time, I feel to come to you. I go take flight, and I go fly to you. As you day waste time, I feel to come to you. Salty love, oh girl, you got me wanting more. I can't get enough of your salty love. Oh girl, you got me wanting more. Mash it,
This is the science show with Dr. Dada. It's just so nice, you cannot do without. This is the science show with Dr. Dada. It's just so nice, you cannot do without.
Well, hello, and welcome to the Science Show with Dr. Dada, right here on Jambo Radio Scotland, broadcasting from the city of Glasgow. Well, as it's been said, the whole of science is nothing more than a refinement of everyday thinking. And that's a quote from an essay by Albert Einstein himself. And this was published back in 1936. But what does that mean? It means that science and scientific concepts originate from common experience, but are sharpened through rigorous reasoning and systematic observations. So why are we talking about this today? Well, the title of today's show is Will Quantum Physics Ever Run Out of Mysteries? Or, in other words, will we ever fully understand how the universe works? Essentially. Well, as I said, this is the Science Show, and I'm Dr. Dada. Today, I'm joined in the studio by Professor Stephen Barnett, and he's a theoretical physicist at the University of Glasgow. Steve currently serves as the Royal Society Research Professor in the School of Physics and Astronomy at the university. And for more than 3 decades, Steve has explored the quantum behavior of light, from twists in the photon's wavefront to ways in which photons can carry perfectly secure messages, and so on and so forth. And yeah, Steve is a mentor to myself as well. He taught me one of my most advanced courses that I did in quantum information. And so yes, Steve is a very, very good person to have with us to discuss this interesting topic today. Steve is also the author of 2 widely used textbooks, and he's a regular collaborator with experimental teams who turn the theory into laboratory reality, if you like. Steve, it's really good to have you with us in the studio today. Thanks for being here.
My pleasure.
Great. So we'll just dive right in. I think the first part of our interview is going to be really about getting to know our guest, getting to know Steve. And we have a couple of questions to help us to do that. So Steve, would you like to tell us how you got into science? Your early education, your early life, how did it go? Say primary school, secondary school, for example. Let's start there.
As I was brought up in the 60s, I think like a lot of people, I was enthralled by two things. Early science fiction on the television, Doctor Who and stuff like that, but mostly the space race. Of course, that happened throughout the 60s with the Apollo program, culminating with the landing on the moon in 1969, and I was greatly excited by this. And it gave you the idea of a sort of scientist or engineer as a hero character, and that really coloured all my upbringing.
I see. That's interesting. That's really, really nice. And at what point did you realize, okay, quantum is where I belong, so to speak?
Yeah, that's a tougher question. It has to do, I think, with why I did a physics degree in the first place. At school, you learn about, you get to touch some of these ideas, some of these concepts, but never really delve into them. And I left school with two burning questions that I wanted to know the answer to. One was, I know I'm not allowed to know in quantum mechanics where a particle is and how fast it's going at the same time.
Yes.
But it must be somewhere, and it must have a speed. That was question number one.
Yeah.
The other question was a bit more subtle. It was, I'd heard of things called charged black holes, and I was also told that light couldn't get out of a black hole. And if light carries electromagnetic signals, how do you know the black hole's charged? And those were the two questions that I went to university at physics to study physics and find out the answers to.
Interesting.
The second one, actually, I now know the answer to. The first one, I always say I'm still working on.
I see. Would you like to share the answer with us briefly?
Essentially, it's to do with the fact that things appear to slow down as they enter towards a black hole. So if you're observing something going towards a black hole, it would appear to be moving towards the horizon but never quite get there.
I see.
And so that's the sense in which the presence of the charges is still felt outside, even though it's already passed into the black hole. That's it. That's why that works.
Amazing. Isn't that fantastic? That's great. It's amazing how you can ask these big questions. We're, so tiny on this tiny speck of dust, this tiny planet, but we can ask these big questions that are so much bigger than we are. Wow, amazing. So in your career, you spent more than 30 years. I'm
afraid it's more than 40.
More than 40 years. Wow. Pushing the boundaries of quantum optics, quantum information, and so on. So what would you say? I know you kind of hinted at one aspect of it already, but what would you say still surprises you or frustrates you, maybe even when it comes to these subjects? Something that keeps you coming back to the drawing board, if you like.
Quantum mechanics always has the ability to surprise, which I think is what keeps us going in research.
Yes.
You do develop after a while a sort of instinct for the way it's going to work based on experience, just like anything else. But it isn't an instinct which is rooted, as you were saying, in everyday experience. And so there's always the capacity to find things which surprise. They don't quite fit. And when that happens, you learn something.
Yes.
When something doesn't quite happen the way you were expecting it to, that's an opportunity to learn something. Yeah.
Yes, absolutely. And do you think, just to jump the gun a little bit, we're going to talk about that a little bit more later on, but do you think we will ever, basically just hinting at the answer to the question, the title of today's episode, do you think there's such a thing as understanding everything about how the universe works? Do you think it even makes sense to say that, or what's your take?
People used to talk about the theory of everything, as if you could write down one big equation that would describe the workings of the universe. And there might be some super equation like that. But that doesn't explain why certain phenomena happen. It doesn't tell you why the things that you see in everyday life are as they are. The equation isn't that solution. And so there will always be more questions. There will always be features of arrangement, and there will always be phenomena that are mysterious that have to be explained. At least we hope so.
Yes. Yeah. And it keeps, as you said, keeps us happier, doesn't it?
And in gainful employment as well.
Yes,
Yes.
exactly. Because I know a lot of people who maybe are not in STEM don't quite know how it works in this, science, in actually doing science. There may be this idea that scientists know more than they actually know. They assume that scientists maybe kind of understand pretty much how everything works. What do you think about that?
Oh my! No, it would be nice to give that impression, but it's so far from the truth. So much of what we do is driven by what we do not understand. So we can explain an awful lot of phenomena. In that way, I think what we do in STEM is useful to society. But we're always driven by the extra pieces which we do not understand.
Yes.
And that's what keeps coming us. Was it Einstein who said something like, if we knew what we were doing, they wouldn't call it research? And I think that's spot on.
That's very true. Exactly. So that's the idea. I mean, I think that's a good takeaway message, isn't it? So maybe a little bit about the, quantum information, quantum science and technology, the year of that is. So with 2025 declared as the year of quantum science and technology, what do you hope that the public takes away about quantum's role in everyday life? And where do you see the next breakthrough coming from?
I think so much of what we perceive or what we do in everyday life is very far removed from the way things work. So most of us carry a mobile phone, but we may only have a very superficial understanding of the way it works. And the more we get into the quantum realm, the more I'm afraid I think that's true. But the key point to take away, I think, is that there is both a challenge and an opportunity of going into the quantum domain. The quantum domain is fundamentally about the very, very small, single atoms, single photons, and so on. And so in some sense that's the limiting territory. No device will ever get smaller than an atom, because that's the building block of matter. And so we're reaching the situation where we're really pushing down towards the most fundamental levels and trying to extract from the phenomena we find technological benefits. It's a very exciting time. The device that people talk about most, I suppose, is the quantum computer. And really the quantum computer will make a dramatic change. I'm not sure we'll see it in everyday life, at least not to start with. And it will make a dramatic change because of two things. One, as listeners probably know, as computer technology has developed, components have got smaller and smaller. And we're reaching the situation where we're into the quantum domain. So small have the individual components become. And we're thinking about the analogues of transistors, which have only one or two atoms and so on in them. And so we're into that quantum domain. So we're forced into that region by the advance of technology, whatever happens. But there's also an opportunity. And the opportunity is that the rules by which matter and light and so on behave in this quantum, this microscopic domain, are so very different from those that we experience in our macroscopic everyday lives. And if we can exploit those new and unfamiliar phenomena, then there's the potential for radically new advances. And of course the quantum computer, which would operate in a very different way to our current existing computers, is but one possibility.
Thank you very much. That's really well said. A really nice takeaway message on the International Year of Quantum Science and Technology. So what we're going to do now is we're going to take a short break. And when we're back, our phone lines will be open and you'll be able to call and join the conversation. Perhaps you'd like to tell us which of the scientific discoveries that you know blew your mind the most, so to speak. And to go on the break, we're going to listen to a song by the Kabusa Oriental Choir entitled So So. We'll be right back. Well, this is the Science Show with Dr. Dada, and this song we've just listened to is Soso by the Kabusa Oriental Choir. Hope you enjoyed it. Well, on today's show, of course, as you probably know, we're talking about quantum physics and whether it will ever run out of mysteries. And we have with us in the studio Professor Stephen Barnett. So we'll just take up our discussion with Steve. So we've been talking about the International Year of Quantum Science and Technology, and now we're just going to look a little bit more into Steve's perspective as well, and his career, his background. So I know from our interactions that you've worked with with Rodney Lowden, and would you like to tell us something about his contributions and the work that you've done with him, and perhaps how that shaped your own contributions as well?
Yes, so Rodney Lowden, in some sense, framed the subject. He wrote, as early as 1973, the first edition of a really seminal textbook called The Quantum Theory of Light. And this really explained, in terms that are accessible, I think, to a student, what the points are, the key points about quantum phenomena, especially as they're associated with light. And that was really the stage at which the field of what we now call quantum optics started. So it was very influential in that way. And I worked with him for well over 30 years on all kinds of problems. Properties of light although quantum properties of light that don't appear in the sort of normal macroscopic world was a big topic. But also practical things like something called quantum cryptography, which you may have come across. And this is the idea to use quantum phenomena associated with light to be able to communicate in such a way that listening in is impossible. It works basically on the idea that a photon, or a short pulse of weak light, is sufficiently delicate that if anybody tries to measure, say for example, what its polarization is or one of its properties, they will create a disturbance. And you can use that disturbance to see that somebody has been listening. And so, of course, if there isn't a disturbance, then you can infer that your message is secure. And also in particular, what I was mentioning before, you may have come across the idea that quantum computers can challenge security by being able to break into our secret techniques at the moment, our mathematics-based secrets, mathematics-based secure communication. But quantum cryptography is secure against that, and so this is like a next generation of secure communication, which is already being developed by a small number of companies and also by communications laboratories and communications companies around the world. And Rodney worked with the researchers at BT, at British Telecom, for many decades. Yeah.
Wow, that's fantastic. I didn't know that. That's really, really interesting. So, could you share with us what your sort of PhD studies were like, and was Rodney a part of that? Did you work with him in any capacity during that period?
No, I knew Rodney through his book.
Okay.
I did my PhD at Imperial College with Peter Knight on something which was called the Rydberg maser, but really it was the idea of what would a laser look like if the gain medium, which produces your amplification, was just one atom.
Wow.
And there were experiments going on in Germany and in France about that at the time. Serge Haroche in Paris ultimately won his Nobel Prize for work on that. Rodney was my PhD examiner.
Oh, interesting.
And we started working together shortly after that. Yeah,
that happens, doesn't it?
About 40 years ago.
I see.
Yeah.
Wow, that's amazing. That does happen. You get an examiner, and because they've spent that much time reading the thesis and so on, it's not uncommon that collaborations kind of start from that, don't they? Wow, interesting. And in all your years of working on quantum theory, has there ever been a moment when you thought, wow, that can't possibly be true, and yet it is? Has there ever been a moment where you're like, you discover something that's so surprising that you basically knocked your socks off, so to speak?
There have been 2 or 3 occasions which have been remarkable, but that's not usually the sensation of knocking the socks off. It's more along the lines of, frankly, you idiot. because it sounds glib, but it's important, because I'm a great believer in the idea of simplicity. And if you really if you've really finally got the point, the explanation should be simple. And so simple, in fact, that you should have seen it many years ago when you started worrying about the problem, if only it were that convenient. And so that's usually that has been how it has worked. It's you idiot. You could have seen this 4 or 5 years ago if you only thought about the problem in the right way.
Wow.
Yes, there have been, I think, 3 occasions in which that 3 times in my career in which that happened.
I see. Would you like to share one of them with us, just briefly?
Yes. Let me think which would be the right one to do. Yes. So there's a more than century old problem, which sounds esoteric, and that is what happens to a pulse of light when it goes into a transparent medium. Think about a piece of glass. Now, light carries momentum with it. It has energy and it has momentum, so it has a push. And the question is a very simple one. When the pulse of light goes into the medium, does the momentum increase or decrease? And 2 very eminent scientists at the beginning of the 20th century, Hermann Minkowski and Max Abraham, both thought they'd solve the problem. Minkowski said it goes up, Abraham says it goes down. And experiments and theory have been arguing about it pretty much ever since, until, not wishing to sound immodest, until I figured out what was going on in 2010. And the bizarre realization was it actually does both.
Wow.
It's a very democratic solution. Listeners may have heard of the principle of the idea of wave-particle duality, that quantum particles can sometimes behave like a wave and sometimes behave like a particle, and that's this quantum idea. And that's true of photons as much as any other particles. And the simple resolution was that one of the momenta, the Minkowski momentum, is the wave momentum. The other one, the Abraham, is the particle momentum. And that just falls, it's as simple really as sort of mathematics behind it, but the ultimate answer is as simple as that. It's a very democratic solution. They're both right. But they were essentially dealing with different questions.
Wow. Amazing. That's thanks very much for sharing that with us. And we'll come back to some physics in a moment, but listeners may be intrigued to hear that you studied the viola or viola. What's the right pronunciation? Is it
viola?
Viola.
Yes. I'm an enthusiastic but untalented orchestral viola player. Yes.
So, what would you say that does for you? How do you approach it? Is it more of something that just keeps you, like a mental reset, something that you do just when you feel like it, or is it something that you actually need to keep you going, as it were?
No, it's an outside. Everyone needs outside interests. I'm an orchestral musician, so I play with the Glasgow Orchestral Society. Those who are local in Glasgow may like to know we do 4 concerts a year in various venues, including the new auditorium, the Royal Concert Hall, and also on the south side. And it's good to have a weekly commitment to go and play with other amateur musicians and do something that's a little bit different. Yeah.
Yes, indeed. That's a really, really interesting one. And maybe one of these days I'll come along and and enjoy the orchestra, the performances.
I'll save you a ticket.
Great. I'll take you up on that, Steve. Very nice. So going back a little bit to physics, toward physics. So your research hobby, you seem to have not just an outside interest, but when it comes to research, you also have a hobby list, and that includes, if I get it right, general relativity, low temperature physics. So how have those detours, so to speak, influenced the way that you frame problems in the mainstream quantum theory that you work on?
The currency that we work with is ideas. And being a theoretical physicist means that I'm not constrained by needing to have particular pieces of equipment, or I can only work with various branches of physics. It's all there to be explored. And I've found that this is something you can usefully do. Something which is a nagging problem in one field, when you look at it a different way, is already solved in another. But also, I think it's good to spend, or at least I found it to be good to spend some of my time thinking about some of the big problems, some of the difficult problems, because they'll only get solved if people can invest time in them. You can't spend all of your time hoping for the eureka moment where you crack something important, but not to have that as a background interest, I think is limiting. So we've recently, may I say something about the most recent?
Please.
The most recent interest has been in magnetism.
I see.
And the fact that some of you may have seen the famous experiment or demonstration of something called diamagnetism, in which Andre Chaim used a large magnetic field to levitate a frog, to cause a frog to move away from the field. And this diamagnetism is a very bizarre and a really unexplained, or largely unexplained phenomenon. And one of the worries about it, which has been known for, again, about 100 years, is that it looks as though, superficially, that diamagnetism is not a causal effect. Now, causality is the simple idea that effect is always preceded by cause. So the cause, then the effect. And that's what we call causality. Very simple, you push on something, it moves. It doesn't move before you push. And for subtle reasons, it looks as though diamagnetism violates this principle. And there have been a number of explanations of why, or attempts to explain why, obviously that can't be true, but that's what most recently I've been exploring with my colleague Nick Vesterberry, who's a brilliant research fellow in my research group.
Indeed, yes.
So, and I think we've cracked it. But don't ask me to explain, because this one's really complicated.
No problem. The paper is out there. I think I saw it recently.
There, yes.
So, if you're interested, you can find that out online. You can read more about it. Yeah, it's really good. So, it's quite interesting. So, there's general relativity as well.
Yes.
There's always, I think, a lot of people who've been following science and popular science channels. They probably have heard about the fact that quantum physics and general relativity don't always see eye to eye, if you get what I mean. So if you had to choose one of these theories, which one would you choose? And I think I probably know the answer to this question. But
I mean, the problem is that their domains of application are so different. And so it's actually quite hard to decide one from another, because they are so very dissimilar in the way that they're put together. But even then, even before you get there, there are profound issues. I hope my colleagues won't mind me saying so. There are profound issues with general relativity and cosmology. There are big questions we don't understand in cosmology, which is fun to play with.
Yes.
One which you might have come across is this idea of dark matter.
Yes.
Which is supposed to be present in very large quantities to explain the motions of galaxies, the fact that galaxies often appear as spirals. The trouble is, nobody seems to know what this large quantity of dark matter actually is, or indeed where to look for it. The particle physicists are doing their best, but as far as we can tell, there is no indication of that it's really out there. And so one does wonder if at least there's the possibility that perhaps there has to be some sort of tweak to general relativity in order to take account of the observations, other than the introduction of dark matter. And then there's dark energy and various other features associated with general relativity as well, which are really rather mysterious. And so, yes, there are lots of interesting questions that you can ask about cosmology and general relativity. So I spend some of my time playing with those as well. So far, no breakthroughs, I'm afraid. Nothing to report.
Yeah, it's very, very interesting. You hear I've heard so many talks, and a lot of brilliant physicists and mathematicians, if you like, think about this problem of taking quantum physics and general relativity and somehow finding a resolution between where they differ.
I mean, I think that the real problem with that is that we mentioned that quantum physics is about the physics of the very small. General relativity is applied on the very large scale, solar systems and galaxies. But also, quantum mechanics is about things like very small masses, whereas general relativity, very large ones. And so it's entirely possible that it's only in extreme situations where you have very small, very massive objects, black holes perhaps, that you can start to probe experimentally in this interface reason between general relativity and quantum mechanics. And of course we can't do that in the laboratory.
Yes.
So it's difficult.
It is challenging, isn't it? One area where people like to cite is when it comes to measuring quantum particles, especially entangled systems. So you've got these two photons, they're worlds apart, and you measure one and the other one collapses to a corresponding result. So the question is, some people are still very uncomfortable with the fact that it seems the correlation between them kind of violates special relativity, the speed of light, if you like. So that collapse seems to happen faster than the speed of light. So do you have any thoughts on that for those of us who know maybe a bit less about it?
Yeah, it's intriguing. It's one of those problems that really bothered Einstein throughout his life, throughout his career. This idea of as you said, two distant particles, you measure one of them and then the state of the other one collapses instantaneously, much faster than a speed of light signal. There are some sort of fixes. So one is that you can prove that behavior cannot be used to communicate.
Yes.
And the reason being that the person whose particle state is going to be collapsed by a distant observation, they cannot detect the fact that it's been collapsed. And so you can't use it for communication. So that there isn't a communication problem as such.
Yeah.
That's what something called the no signaling theorem. But it also strikes very much, I think, at the way in which we perceive what a quantum state is. So the language we glibly use is that these two particles are in what we call an entangled state. But that's really just a code for that's how we are going to describe how the correlated phenomena behave. We talk about wave functions, but it's not a wave function except by analogy in the same way that we understand, say, for example, a water wave or a light wave. It's a probability wave.
Yes.
And that is really something that we know how to do the mathematics of, but there isn't really any analogous feature in the macroscopic world with which to understand it. And that's part of the mystery, it's part of the joy of doing quantum physics, because I think that's something that we may never fully get to grips with, apart from as a calculational tool. to actually know what a state really is. And it's great fun for the philosophers as well, because there are any number of physical analogies, explanations of what this might mean, but quantum mechanics doesn't, and the physical systems themselves don't care. They just behave the way they behave, and if we don't understand it, that's our problem. You know?
Interesting. So yeah, that's a very nice take-home message, isn't it? It works the way it works, whether we understand it or not. It doesn't depend on whether we understand it. So that's quite interesting, an interesting thought. And with that, we've come to our next music break, and we're going to be listening to the Kabusa Oriental Choir once again, this time Jerusalema. And we'll be right back.
Break it down now. Where are my praises? Are you ready to do this with me? A 1, 2, 1, 2. Jerusalem, Ikayalam, Ilondolos, Jerusalem, Ikayalam, Ilondolos. One more time. Jerusalem, Ikayalam, Ilondolos, Jerusalem, Jerusalem. We're about to take this to the next level. Lift your voice.
Fantastic. That was Jerusalema. Not quite the one I mentioned about the Kabusa Oriental Choir, but another version of Jerusalema, of course. And this is the Science Show with Dr. Dada on Jambo Radio Scotland, broadcasting live from the city of Glasgow. I'd like to take this opportunity to shout out to our sponsors and supporters on this show, including IOP Scotland, University of Glasgow, the EPSRC through the Impact Acceleration account from the University of Glasgow, and of course the Royal Society. The Royal Society funds our research, and of course, as you know, Professor Stephen Barnett, who we have with us in the studio, is also a Royal Society research professor as well. So shout out to all these organizations who in one way or the other support what we do here, of course, and most importantly the science that we actually do. And of course, you can always catch the show. You can catch the recorded version on YouTube if you go to our YouTube channel, Jambo Radio Scotland, and also you can listen to us live on DAB and through jamboradio.co.uk, and as well as the app. Great. So we'll just have a little section of an interview, and then after that, to conclude the show, we're going to have a STEM wrap of the week, which is going to be very interesting to look forward to. Feel free to join in. We'll see how that goes. But we'll take a few questions to wrap up our interview first. So, Steve, I was wondering about this question. I thought I would ask you this one. So this idea that quantum physics or physics in general isn't just about particles, but also about information. When would you say that shift in thinking happened? And how has it shaped your research?
I think really the development of and the study of quantum cryptography and quantum communications has been key, because that was the stage at which two disciplines which had really been quite disparate until then came together, namely quantum physics, and which was of course the domain of the physics departments, and communications theory, which was really a branch of effectively electronic engineering. And when these two communities came together, it became apparent that there was something subtle going on to connect them, and that really was that what the engineers had called information, and what Claude Shannon introduced as information to explain how communication works, has a twist to it in quantum mechanics, in that quantum information is not the same as classical information. And in some sense, it's been trying to work out what that difference means that has defined the progress of the field into what has really become quantum technologies, quantum computing, quantum communications, and so on. So I think it was really at that point, and that would be, let me think, not so very long ago, of the order of 20 years ago.
I see.
That this happened. I remember I attended the first international conference on quantum communications that was ever organised, and the entire international community turned up, plus people from the classical side, the engineering side, and in total there were 40 of us, and that was the world's community at the time. Now every physics school seems to be overflowing with specialists in this particular area, and so it's because it's become so important.
That's very interesting. Thank you very much for sharing that perspective with us. It has grown so much, hasn't it, in the last 20 years or so? I remember in the 2000s, the kind of papers that came out then are very different from what you see now. It was like when people started talking about entanglement measures and all these kinds of very interesting things, like finding out exactly how to actually make sense of this whole idea of quantum states and so on. But now it's more spin outs that you see, and people kind of
this is part of the natural development.
Yes,
we worked through the fundamentals. We thought about the possible applications. Experimental demonstrations have come along, and now we're actually at the stage of trying to move over into the practical applications, to the realistic devices. And it's for that reason, a very exciting time. Perhaps not quite so exciting for theorists like me. We've done our bit, but certainly as the development comes along, and we can start thinking in terms of devices and really a technological change, which might ultimately affect people's lives, which would be very nice.
Yes, indeed. Thank you so much. Thank you so much for joining us on the show today, Steve. It's been amazing. I wish we had 2 hours, and we might as well, get you back on the show in future. That would be fantastic. Thank you very much for sharing these unique perspectives on the field, as well as what lies ahead as well. So I put together a very short song and rap about what we've been talking about. So wave particle duality, quantum physics, and mysteries and all that stuff. So it's entitled Quantum Rules, and we'll ask the DJ to hit us with the track, and we'll see how this goes. Yeah, okay. Atoms bounce, they don't stay still. Tiny world, but it's real. Spin and charge, up and down. Ghosts of matter all around. Light's a wave, light's a particle. Both at once, what a spectacle. Look, it will change. Measure it, it won't be the same.
Quantum rules, we don't know why. We keep asking the how and why. Will we learn maybe one day, but the mystery won't go away. Quantum rules, we don't know why. We keep asking the how and why. Will we learn maybe one day, but the mystery won't go away.
Cat is dead, cat alive. Both at once, still it thrives. Clock ticks weird, near a star. Time and space ain't what they are. Particles talk from far apart, linked like minds, heart to heart. We try to see, we try to know. The truth is deep and hard to show.
Quantum rules, we don't know why. We keep asking the how and why. Will we learn maybe one day, but the mystery won't go away. Quantum rules, we don't
Feel free to sing
know why.
along.
We keep asking the how and why. Will we learn maybe one day, but the mystery won't go away.
Big or small, it's all a quest. We keep searching, we do our best. The more we know, the more it's strange. Quantum world don't ever change. Come on.
Quantum rules, we don't know why. We keep asking the how and why. Will we learn maybe one day, but the mystery won't go away. Quantum rules, we don't know why. We keep asking the how and why. Will we learn maybe one day, but the mystery won't go away.
And that's it. That's what I've got.
Very good.
Great. Thank you very much. And that brings us to the end of our episode today with Professor Stephen Barnett. And of course, this is the Science Show with Dr. Dada. And of course, you know, this is where you need to come to learn about the developments in STEM when it comes to Scotland. And of course, we'd love to hear from you. We'd love to hear your questions, thoughts, comments about today's show. So reach out to us on our social media channels. And a big thank you to you, our listeners, for tuning in and for keeping those radio dials locked. And this is Dr. Dada saying, stay curious.
Mwana mutu wa